8.1, radioactivity. Yeah. In part A, I want to give you 3 application problems. Yeah. Yeah. Very simple, yeah. But we need to use the problem-solving mentality to understand, to learn these 3, how to solve these 3 problems. Yeah. Word problems. Yeah, we will have many word problems. Yeah. So for each of our home assignment, you will have some equation problems. Yeah, not all word problems. Yeah. The first few questions, just math equation problem solving. Yeah. But after that, you will have quite some word problems. Yeah. So here we will have 3 word problems. Yeah. All right, so let's start our first word problem. The background is the radioactivity. All right, let's start. All right. Yeah. First, before we solve these 3 problems, let me go through our typical problem-solving procedure. Yeah. All right. Our objective of this class: develop problem-solving skills for the engineering problem. Yeah. So the problem-solving skills, yeah, that's the main focus of this class. Yeah. We will focus on the understanding, on the analysis, the thinking, yeah, lot of things. Yeah. There are many special strategies. When we do problem solving, we need to apply a lot of strategies. Yeah. So all those things we need to learn in this class. All right. For engineering problems, that means an application problem usually with a physical nature. Yeah. So we need to have sufficient physics background. Yeah. Yeah, because most of the time we solve those problems related to the physics laws. Many physics laws we need to apply. Many physics laws. Yeah. All right. Yeah. So these 4 steps in our problem-solving procedure. First, when we have a word problem with physical nature, yeah, we need to understand that physical system. First, the understanding part, the physical system. Yeah. Yeah. We need, from the given problem, we need to know related physical concepts. Yeah. Yeah. And the physics background you need to use to understand the environment, that system. You need to understand that system. So that background knowledge, important. Yeah. But we do not need too much. Okay? Yeah. All right. Yeah. Then, after that, second step, we need to build a mathematical model. Now we need to work on problem solving. We need to solve the problem. How to solve the problem? We need to apply some mathematical model. So what's that? We need to apply certain physical laws. Newton's laws, so many different physical laws. Yeah. Electricity, you know, yeah. Many laws. Yeah. All right. Using those laws, we can set up differential equations. Yeah. Yeah. All right, that's the mathematical model. Yeah. So we will, after that, after the modeling step, we will get a PDEs or ODE. Yeah, most of for this class, most of the time ODEs. Yeah. But we will learn also some PDE cases. Yeah. Yeah. After the modeling, then we need to solve differential equations. Yeah. So then we need to apply various mathematical techniques, yeah. Problem-solving techniques. Yeah. Yeah. So there are some standard methods, yeah. But sometimes it may not be that obvious which method to apply. Not that obvious. So you need to do a lot of transformations. Yeah. So this part also not easy. Yeah. 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 Step 3, the last step, physical interpretation. After you get a solution, you need to interpret. So what's the meaning? You need to get back to the original question to explain your final result. Yeah. So that's the last step. Yeah. Yeah. Because some of the solutions does not make sense, you need to drop it because you may have multiple solutions. So some of the solutions, when you get back to your physical environment, it does not make sense. So you need to drop it. Yeah. So you need to make appropriate interpretation. Yeah. All right. So then, do some necessary work to finalize your solutions. Yeah. All right. So that's the standard problem-solving procedure, yeah, for this class. Yeah. Yeah. For us, actually, we will not do too much on the last step. Yeah. Last step is important. Yeah. Here, just to let you know. Yeah. Yeah. But for us, because our problems are relatively easy. Yeah. Our problems not very complicated. So after you complete the first 3 steps, not much to do, the last step. You can make your conclusion immediately. Yeah. Not much to do in the last step. Yeah. Yeah. All right. Yeah. So next, we try to, follow the standard procedure to solve our remaining word problems. Yeah. All right. The first one, problem 1, radioactivity. Yeah. The background from radioactivity. First, let me describe the question. Given 1 gram, 1 gram of radioactive substance, radium. Okay? Radium. Yeah, this one. Yeah. Here, you need to know a little bit about this substance. Okay? Radium. Yeah. Yeah. I will talk about that. Yeah. Because the background is important. I will give you that information later. Then, find the half-life of the radium in years. Half-life, one concept. Yeah. So before you can solve it, you need to understand all the related concepts. Here, there is a half-life concept. Yeah. Find the half-life of this radioactive substance. That's the question. Yeah. But here, that's the whole question. Yeah. But you need some more information to solve. Yeah. Because from the given information, it's not enough to solve. You need one constant You need one special constant related to this substance, this radium substance. This is one of the isotopes of the radium. Radium has many isotopes. So this one is one of the isotopes. Yeah. For different isotopes, they have different constant. Yeah. So you need a special constant corresponding to this particular isotope. Then you can find a half-life. All right. But let me give you more information before we can find a solution. Yeah. So you can see the first step, understanding, is very important. Otherwise, you won't feel comfortable, right? At this point, I feel most of you do not feel comfortable working on a solution, yeah, because you do not understand a lot of things here. Okay? Yeah. The first thing, let's understand that half-life concept. Yeah. The time, yeah, some time period, the time in which half of the given amount of radioactive substance will disappear, given amount 1 G, 1 gram, 1 G, okay? Half of it disappear, 0.5 gram, okay? After a certain period of time, because it's radioactive, the substance will change, right? Yeah. Change to different substance. After that, radioactive, reaction thing, So here we do not need to go that far. Yeah. We don't worry about how to do the radioactive reaction, that part. Just it changes to different substance. Yeah. Then we want to know how long does it take. So this radium-226, this particular isotope, the amount of this isotope is reduced to 0.5 gram. That's the question. But there is a hidden substance should be given before we can find a solution. Let me talk about that hidden constant. Here, we need to apply some physical law here. So what is the law? Yeah, the modeling part. We need to do the modeling part. Step number 2, modeling. The time rate of change. Yeah. Y prime derivative of y function. What is the y function? Yeah. Here, you want to, what's the y function? The amount of radioactive substance, right? The amount of radioactive, that's the y. That's our y function. Amount of radium, 226, that amount, y function. Because that amount, that function is a decreasing function, right? Reduce, keep reducing, decreasing function. Yeah. At the beginning, it is 1 gram. Then, after a certain amount of time, it becomes 0.5 gram. Yeah, there is a function. Yeah, we need to find that function, find that y function. All right? Yeah. Okay. But there is a physical law on that y function. What's that law? The law given here. Derivative y prime of t, that's the time rate of change, is proportional to original y function. This is the law. Okay? Yeah. Someone discovered it, yeah, by doing a lot of physical experiments. Yeah. Then, observe this physical law. Yeah. Now we just take it. We apply it. Yeah. All right. Based on this law, we can write a differential equation. All right. This is the differential equation. dy over dt. Derivative of the y function equals negative K times Y, proportional. Yeah, we know proportional means some constant multiple of, right? That's the proportional. What's the meaning of proportional? Constant multiple, okay? Yeah, but the constant multiple here, why use negative K? Because in order to see decay, right? So negative refers to the amount is decreasing, decay, decreasing. So we use negative. K should be a positive number. K should be a positive number. So negative positive constant K times Y function. That's our equation. Yeah. And K should be given. K, that's the hidden constant. That should be given related to the isotope, radium-226. Yeah. Here, K is given. 1.4 times 10 to the negative 11th second, hertz. Yeah, you can call it hertz. 1 over second. Yeah. The constant. Now we have enough information to solve the problem. We can find half-life. We're ready to find half-life. Okay, all right. How to find it? Yeah, next question. All right. So this is, we call it decay constant, this K, decay constant. For different isotope of the radium, its decay constant is different. Yeah. Okay, all right? Yeah. Yeah. Where the value K is known? From experiments for radium-226. Yeah. All right. Yeah. Here, there are two numbers. Yeah. Next slide, I will explain these two numbers. Yeah. Yeah. If you have questions, yeah, next slide I will explain these two numbers, the meaning of these two numbers. Yeah. Yeah. All right. All right. And here you can see this physical law is very important for this question. Yeah. For our part A, the title of our part A, the decay model. Yeah. So now, the whole decay model, this topic, relies on this physical law. This physical law. Okay? Yeah. 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 So people summarize this physical law and call it radioactive decay law. So this law, yeah, the first time people call it radioactive decay law. Yeah. Yeah. Because this law was first discovered when people studied radioactivity. Okay? But after that, not necessarily radioactive substances, only radioactive substance has the decay phenomenon, right? Many other things, a lot of different phenomena, they also have the decay property, right? Yeah. Yeah. If any phenomenon has the decay property, then we can apply this law. Okay? So we can generalize this law to the general decay model. Okay? Yeah. So later, yeah. So because the next a few questions you can see, yeah. So we have different type of questions, not necessarily radioactive questions. Yeah. All right. The background, a little more background. First, we need to understand the half-life concept. Yeah. All right. The general meaning, yeah, the time required for a quantity of substance, yeah, to reduce to half of its initial value. Yeah. All right. The half-life concept. But later, we will also generalize this half-life concept slightly. Yeah. Yeah. Our second question, you can see a certain kind of generalization. Yeah. In that generalization, we will not use time. Here, we use time. Yeah. That one, we use height. Height. Yeah. Half of the height. Yeah. Yeah. But we do not call half-life. Yeah. Yeah. But a similar approach. Similar approach. Yeah. All right. The term is commonly used in nuclear physics to describe how quickly unstable atoms undergo radioactive decay, or how long stable atoms survive. Yeah, here, the stable thing. The stable thing, unstable and stable thing, yeah. We can connect the stability of the radioactive substance to half-life. Yeah, half-life. Yeah. Because in this radium, there are many isotopes. Some of the isotopes very stable, some of the isotopes very unstable. Yeah. Based on your intuition, yeah, do you feel the stable isotope should have longer half-life, or unstable isotope should have longer half-life? Yes, stable. Yeah, stable. Yeah. So decay slower, right? Yeah, stable. Yeah. Unstable, decay very fast. Yeah. So shorter half-life. Yeah. Yeah. Things like that. Yeah. All right. The term is also used more generally to characterize any type of exponential decay. Yeah. So here, this tells us we can consider, all the decay phenomenon, but decay, we consider mainly the exponential decay phenomenon. Yeah. Yeah. Not necessarily radioactive decay. Yeah. So any kind of decay. Yeah. 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 But for this model, we only consider exponential decay. Polynomial decay, logarithm decay, yeah, we do not consider. So this model does not include decay other than exponential decay. Yeah. All right. The property. Yeah. Half-life is constant over the lifetime of an exponentially decaying quantity. Yeah. All right. Yeah. So that's the background part. Now, yeah, a little more background. Understand the radium substance. Yeah. Let's understand the meaning of 226 and 88. Yeah. All right. The pure radium, silver white. Yeah. So you can see the radium substance here. Its atomic number is 88. Atom, yeah, yeah. In its core, the atom, 88. Yeah. Atomic numbers. That means it has 88 protons. 88 protons. Okay, all right. Then, yeah, so this is the periodic table. Yeah. The radium is here. Yeah, 88 in this location. Yeah. All right. And yeah, so then neutron. Yeah. So here, this 226, that's the sum of the number of neutrons and the number of protons. adding together, that's that number, 226. Neutrons. All right. Then the properties. Here, this is another isotope. 224. Different isotope. So this isotope, you can see there are this many neutrons, 136. Protons the same. All 88. Same. So here, these two numbers actually determine different properties. 88, this number determines the chemical property. The number of protons determine the chemical properties. Okay? And that number determines the physical property. So all these different, so here you can see all these different isotopes of the radium, they have the same chemical properties, but different physical properties. Because the same atomic number, 88. All right. All isotopes of radium are radioactive. Or how many? So I searched, I found there are 34 isotopes for the radium. 34. All radioactive. But with different half-life. All right. The most stable isotope. So our current, this one is the most stable one. Half-life 1,600 years. Longest half-life. Longest half-life. All right. But what is the most unstable isotope? I also searched most unstable. Most unstable. That's the 216. Isotope. What's the half-life? Half-life is very short. The half-life is 182 times 10 to the negative 9 second. Nanosecond. 182 nanosecond. That's the half-life. In that short period of time, quickly reduced to half, disappear. Quickly disappear. All right. So that's the information we. And this one, this isotope, the half-life, 3.6 days. All right. But here, just to give you some, simple background. All right. Next, because our goal, we want to solve the problem. Okay. All right. So what mathematical tool can we use here? To solve the problem, we need to apply mathematical tools. This is our first class. We haven't learned any tool at this point, right? So at this point, nothing. So we have, our toolbox is empty at this point. But we need to build up. Okay? We need to build up. Put a lot of tools in this toolbox. After we finish this class, so we want to have a lot of tools to solve the problems. Yeah. All right. Yeah. But this problem is very simple. Yeah. We do not need some fancy tool to solve. Yeah. All right. Yeah. So here, but we need something. Yeah. You need something to solve. Yeah. All right. First, set up equation. Yeah. Yeah. We did that, right? Yeah. By the physical law, by the decay law, right? Yeah. By the decay law. Yeah. So we have this equation. So we complete that step, modeling step. Our next step, we need to solve this equation. Yeah. Yeah. I believe some of you may already be able to solve this equation. Yeah. But here I want to start from scratch. Yeah. Even if you know how to solve. Yeah. Some of you, I believe, you know how to solve. Yeah. But here, I use a different view to look at this question. Y function is the amount of radium substance. All right. Step 2, solve the first order. Yeah. This equation we call the first order differential equation. First order ordinary differential equation. Yeah. Ordinary. Yeah. ODE. Yeah. Differential equation. Okay? All right. All right. Yeah. Oh. Oh, yeah. Now, I want to look at the solution. Yeah. Yeah. When I look at the solution, yeah, I want to look at a little general. Yeah. Yeah. dy over dt equals any constant c times y. Let's consider this a little more general case. C could be negative, positive or negative. Yeah. But a C should not be 0. Yeah. Should not be 0. Otherwise, too easy. Yeah. Non-zero constant. Yeah. All right. And C, when C is positive, yeah, positive, then it's not decay, right? Yeah. Derivative equals positive number times the original function, so increasing, yeah, increasing function. Yeah. Negative, that's the decay thing, decay situation. Yeah. All right. Now, at the beginning, because our toolbox is empty, so we have no idea how to solve. Yeah. All right. Now, we need to apply some problem-solving strategy. Problem-solving strategy. Here, I introduce you our first problem-solving strategy. Okay. All right. What's that? Based on our textbook, it is called Golden Rule. Golden Rule of problem solving. Yeah. From the name, it's very important, right? Golden Rule. Yeah. Yeah. What's that golden rule? Yeah. Very simple. What's that? If you cannot solve your problem, try to solve a simpler one. That's the golden rule. If you cannot solve the original problem, you can modify it. You change it to a simpler version and try to solve the simpler version. Is that a good idea? But many experienced problem solvers, they have the experience. It's a very good idea, very effective. So effective, so that's why people call it golden rule. Okay? All right. Yeah. So I'll give you the reference here. Yeah. On our textbook, page 19, step 2. Yeah. Talking about this golden rule. Yeah. And then later, several other situations, we need to use this golden rule. All right. And also, this problem-solving strategy, another place explain this strategy. Yeah. I'll give you a reference. Polya. Yeah. Polya. He's a very famous mathematician and educator. Polya. Okay? mathematician, Polish mathematician, but he was a Stanford professor. Yeah, Stanford professor. Yeah, you know, many years ago, old time. Yeah, he wrote a book. He wrote a famous math problem solving book. It's called "How to Solve It." The title of the book, "How to Solve It." Yeah, yeah. So you can find it from Amazon easily. Yeah, "How to Solve It." Yeah, yeah. Not very thick. Okay. Yeah. All right. In this book, Polya summarized this idea: solve a simpler problem. Yeah. Modify the original problem to make it simpler and to solve it. Then gradually move it back to the original version. Yeah. So this golden rule. All right. Now let's do it. Let's follow this guideline. How to modify it. Now, how to choose a simpler case. Yeah. This is the original problem. A little hard to solve. A little hard to solve. But now you have a chance to make it easier. How do you want to make it a change? To make it easier, you have freedom to change it. Simple way to make it easier. Any idea? Try a little bit. How to change that, how to choose that C? Tell me, what C make it the easiest? C is unknown, right? 0. Cannot be 0. All right? C cannot be 0. What C? 1. 1 is the easiest because 1 is gone. C is gone. Yeah. So the best choice is we take C equals 1. Okay? Golden rule. Yeah. All right? Yeah. Now let's solve this newer version much easier than before because C is gone. Because C is, you know, to deal with C, we feel not very comfortable. Now it's gone. Sorry. Now it's gone. So we feel better. Yeah. Every beautiful form. Yeah. All right. Now let's make interpretation of this equation. How do you interpret this equation? Problem solving based on understanding. Yeah. So this interpretation, that's part of our understanding of the question. Okay. Yeah. Oops. Yeah. Sorry. Yeah. All right. Let me interpret in this way. That equation tells us some function, when you take derivative, its derivative equals itself, right? Y function, when you take derivative, it equals itself. All right, that's the function we are looking for. What function? Its derivative equals itself. E function. Yes. Yeah. Many of you know that. Yeah. So you can find the Y function quickly. Yeah. All right? It's an E function. All right? Yeah? All right. Yeah. Because you plug in. Yeah. Y prime, still E function. Same function. You can see, you can find a solution based on your interpretation. Okay? All right? Yeah. After we complete a simpler case, we need to move back to the original case. Yeah. All right. Next. Yeah. Let us all right. Complete the remaining part of the solution. Yeah. Our goal, because that's our target equation. Yeah. We need to put the C back. All right. The question, where to put that C? Okay, all right, yeah. What do we have so far? We have solution, one solution, okay? Yeah, the solution, that E function, just one of the possible solutions. You cannot say you have all the solutions, right? No, that's just one of the solutions. You may not exhaust all the solutions, right? Yeah. 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 So that's the one of the solutions. Yeah. So you may want to consider more the general solution. Yeah. Some students, yeah, for the online, yeah, you can leave at this point. Yeah. Go ahead. Yeah. Don't worry. Yeah. All right. Think about if you put some constant A in front of this E function. Yeah, any constant A, yeah, but non-zero. We don't want to, put a 0 to kill our main function, right? Our main function is gone. Yeah. So the general case we consider, non-zero constant A. Then also a solution, any A, also a solution. Yeah. All right? Yeah. So because if we have more general solution, then in our real-world problem solving, we have more room to manipulate our equations. Yeah, so it's a better way. Yeah, all right. But after that, we want to factor in the constant C. Factor in the constant C. Yeah. But when you factor in constant C, what is the appropriate location for C? That's important. Appropriate location. Okay, all right. Yeah. So here, we want to try this location. Exponent location. We put C at the exponent location. Yeah. Okay? Because if you put there, you verify it, you take derivative by the chain rule, right? By the chain rule. C times e to the ct by chain rule. Okay? All right. Yeah. Yeah. So the general case, now you can write the general solution. A times e to the ct. The general solution of that target equation. Okay. All right. Yeah. All right. Yeah. So now we can go back to our original question. Original question, C equals negative K. K is given. Now we are ready to solve the original problem. Yeah. So let's, yeah. Original problem has the initial condition at 0 time, at the beginning. Yeah. Yeah. When we start, the substance, amount of substance, 1 gram, y of 0 equals 1. Yeah. All right. So let's use that condition to fix the constant, unknown constant. Yeah. Let's plug in. Yeah. The equation form should be in that way, but C equals negative K, right? Yeah. 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 So here we verify it. Yeah. So no problem. Yeah. We verify it. Yeah. All right. So but then now we want to go back to our K version. Yeah. All right. So we use this, we update our function in this form. Yeah. But the A is unknown, undetermined. We need to determine the A. Yeah. All right. Determine A, we use the initial condition. Y of 0 equals 1. So you plug in t equals 0. When t equals 0, the function value equals A and also equals 1. So A is 1. A is 1. All right? Yeah. So you have your final solution. Y function equals e to the negative kt. Yeah, that's the Y function. That's the amount of radioactive substance for this function, but you do not know the half-life, right? Our goal, we want to find the half-life. So this is not our goal, okay? Yeah. This is an important step, still one step away from our destination. So the last step, you need to solve for the half-life number. All right, calculate the half-life. Half-life, certain time t, you plug in, here I use T1. I let T1 corresponds to the half-life. You plug in T1, Y of T1 equals 1/2 of the amount, that's 0.5. Okay? 0.5 equals e to the solution file, you plug in T1, e to the negative k times T1. Okay? So you solve this equation for T1. K is given. Remember, K constant. The K constant is given. K is given. Only one unknown. T1 is unknown. Yeah. You take a natural log. Okay? Solve for T1. You take a natural log. T1 equals natural log of 2 over K. Then you do the division, plugging, division. At the end, you get your answer. This number, but the unit of this number is second. This number of seconds. Half-life. You find half-life, but in the second unit. But we want to convert to years, right? Yeah, because this number is too large. So we want to convert it to number of years. So the last step, you convert it to number of years, approximately 1,570 years. Yeah. The previous slide, we are given 1,600 years, right? Yeah. So this one, that one is another approximation. It is 1,600. Yeah. Here, based on the given numbers, we get this half-year number, half-life number. Yeah. All right. Yeah. So that's our first class. Yeah. But we still have 2 more examples. Yeah. So next time we will complete those 2 examples. Yeah. But we need to start part B next time also. Yeah. All right. That's it. Then I will post the video. Yeah. So you try to, play around. Yeah. See if there is any problem.